Thank you. I'll start with a short story that happened to me. So it was a normal working day. I came from work to join my wife and daughter for a dinner. And I'm really excited because the model our team has been working on has finally started showing promising results. And I'm really eager to share this with my family. My wife is busy though because she's trying to feed our daughter who is fussy eater. So she doesn't want to talk about models or anything else at that point. But I'm so excited I cannot wait. So I start telling her, like, look, we had this model we built and it wasn't working. And we've been debugging it for more than a month. And finally, turns out that this all was just stupid bugs like typos, like wrong feature names, this kind of stuff. And we finally hunted them enough, so the model now performing as we expected. And so like I shared with excitement and I expect her like, some reaction or something. But she's been busy, she barely listened, but she doesn't want to be rude, so she understands that she needs to do something. So she offering her comments like, oh, nice, this model behaves just like you do at times. And I'm like, what? What do you mean? How it's even relevant? And she said, like, look, when you met at me, you don't simply tell me what's wrong. I have to spend so much time figuring out what's going on, just like you guys with this model. And she's actually spot on. The models are really hard to debug. If you build a model and it's underperforming, it can be a nightmare in debugging. It can cost like days, weeks, or months, like in our case. And the least that we can do to ease the pain is to ensure that the data that we feed to the model is okay. So like the data doesn't contain these bugs. And this is what features platform aim to do. They aim to deliver good data for machine learning model, and feature platforms is what we will be discussing today. My name is Ivan. I'm software engineer at ShareChat. ShareChat is an Indian company that builds a couple of social networks in India, like the largest domestic social networks. And I'm primarily focusing on this data for ML, and in particular this feature platform. And before ShareChat, I had experience working at Meta and ScyllaDB. And one of the social networks that ShareChat builds is called Moch. It's a short video app, pretty much like TikTok. It has fully personalized feed, around like 20 million daily active users, 100 million monthly active users. And the model in the story is actually the model that, the main model for this app. So the main model that defines the ranking, that defines like which videos we will show to users. And today we will be talking about how we build the feature platform for this app, or any app like this in particular. So like we will have the background about what the feature platform is, or what the features, high-level architecture of any kind of feature platform, and the majority of time we'll spend on challenges and how to overcome them based on our examples. And finally, some takeaways. Let's refresh the memory of what the feature is for ML. A feature is pretty much anything we can derive from data. And typically it attached to some kind of entity in the system. For instance, it can be the user as an entity, or post, or creator, which is also a user, but the one who posts the content. And there are multiple types of features one may be interested in. Like, for instance, window counters is like the feature. Give me the number of likes for this post in the last 30 minutes, or give me the number of engagement from this user in the last 1 day, this kind of window counters, because they have time window. There can be lifetime counters. Lifetime is, they don't have windows, so like total number of posts or likes for the given post, or total number of engagement from the given user. There can be some kind of properties, like date of birth for a user, or post language, or this kind of stuff. Or something like last n. Give me last 100 interactions with this given post, or give me last 1,000 engagement for the given user. In this talk, we will primarily focusing on window features. They somewhat most interesting. And to summarize what the feature platform is a set of kind of services or tools like that allows defining features, like give some kind of feature API. They list features and read what they mean. Like they allows like launching some feature pipeline to compute. And finally, feature store is to read the data when it's needed. One important aspect I wanted to stress is that it's really important that feature platform helps in engineering velocity, meaning that it doesn't stay in the way. Instead, it allows for fast iteration. So like that the people who build the model, they can easily define features, update them if needed, or read what they mean. Because when it comes to some kind of investigation, especially what model like underperforming, let's say, it's really important that people can go and easily read, okay, like this is the features that we feed and this is what they mean, and it's pretty clear. So it is not hidden somewhere in like tens of files that in cryptic language or whatever. And in typical architecture for any kind of feature platform, it starts with some streams of data. Like in a social network, it may be like streams of likes, streams of views, video plays, this kind of stuff. Some processing engine that gets the streams of data, computes something, and writes to some kind of database. And finally, in front of this database, there is some service that gets request for the features, transforms it to whatever queries it required for database, it probably performs some last aggregations and returns. And speaking about last aggregations, in particular for window counters, how to serve the query, like give me number of likes in the last like 30 minutes or 1 day. Typically, the timeline is split into pre-aggregated buckets. We call them tiles of different size. For instance, we can split the timeline for buckets of 1 minute, 30 minutes, 1 day. And when the request comes, like let's say at 3:37 p.m., we want like number of likes in the last 2 hours. And we can split this window of 2 hours, cover it by the relevant tiles. And so then we request database for these tiles, get the response back, and aggregate across this tile and return the result. So it's a typical technique to power these window counters. And that was it about architecture. Now let's go to the challenges, solutions that I will be talking about in form of kind of stories. The first story is a boring one. It's about the choice of streaming platform and database. So for streaming, we picked Redpanda, and for database, we picked ScyllaDB. And ScyllaDB and Redpanda, they're like siblings. So they share a lot of similarities. First, they were born with API compatibility with existing systems, like Scylla were born with Cassandra API and later added DynamoDB API, and Redpanda is Kafka compatible. They both obsessed with performance, so they do this via so-called shard per core architecture. So shard per core is when we split the data in some kind of shards, and each shard is processed by a given core in the system. And this architecture allows eliminating like synchronization overhead or like logs, this kind of stuff, and this helps them to get to the performance numbers they desire. It's not easy to build application using this shard per core technique, and they both leverage C-star framework. It's open source framework. It's built by Scylla team. It allows to build this kind of applications. They both don't have autoscaling. It's actually not entirely true anymore for Redpanda. They just announced that they launched Redpanda serverless in one of their clouds. But if you install them in your own stack, they don't have autoscaling out of the box. But despite that, they're extremely cost efficient. So like in our company, we use them not only in this feature platform thing, but actually migrated a lot of workloads to ScyllaDB. Like to Scylla, we migrated from Bigtable, and to Redpanda, we migrated from GCP PubSub and in-house Kafka, and achieved really, really nice cost saving. And last but not least, so they both have like really cute mascots. So like if you work with the systems, that you get to work with like some swag like this one. And that's it about the story, because like these systems are tragically boring so that they just works, and they really seem to deliver on the promise of like operational easiness, because like when you run them, you don't need to tune, so they tend to kind of get the best out of the given hardware. So my view on this is biased a bit because we use managed versions, but we tested non-managed versions as well, and like, this kind of the same. So we tested it, and like we picked managed just because we didn't want to have a team behind this. So that's all. Let's go to the less boring part. So when it came to streaming in database, there were a bunch of options. But when it comes to processing engine, especially at the moment when we made the decision, there were not so much options. In fact, there was only one option. When you want to like real-time stream processing, and what's important, we want real-time stream processing, and we want some kind of expressive language for the stream processing. And so Apache Flink is the framework that can process the stream of data real time, has like some powerful capabilities, and what's important, it has Flink SQL. So like one can define the job in SQL language, and it's really important for feature platform. Because of that property, we want to deliver so that it's easy to write features, and it's most importantly easy to read features. And so we picked Flink, and we can build features using this kind of stream in SQL. So what it does, this query, it basically works on top of streaming data, selects them, group by some like entity ID and like some identifier of the tile, because we need to aggregate these tiles. And this query forms this so-called like virtual table. So virtual because it's not really materialized. It keeps updating as the data comes. So for instance, some event comes, and now we updated like this shares and likes. Some new event comes, we again updated, and this process continues. And so like super nice. Like we build this kind of proof of concept pretty quickly, and like we're happy. By the way, from developer experience, like Flink is really nice. It's easy to write on, like using like developer kind of workflow. But then the question comes, so okay, so like we build this query, we launch the job, it's running, it's updating this virtual table, all good. And now we want to update this table, update the query. And Flink has this concept called save point, checkpoints. So basically, because it's streaming, it's stateful processing, it has some state. And so like what save point does, that we can stop the job, takes the snapshot of the state, then we can update the job and start again, and start from this snapshot. So like it continues working without like huge backlog or something. And so like this was the expectation. Okay, like we have Flink, so Flink has save points. Now we have Flink SQL, so like we can update this SQL and restore from save point. Unfortunately, it doesn't work like this. And in fact, it's impossible to upgrade Flink SQL job. So like, and for us at that moment, kind of unexperienced Flink engineers, like it came like a big shot, because like, come on guys, like, are you kidding? So like, what we're supposed to do? Like we launched the job and should expect it never fails, like works forever or what? Kind of when first shock kind of faded, like and we thought about this a little bit more, it's not that surprising, because like this query actually get translated to a set of stateful operators. And when we do even slight change in the query, this kind of stateful operators may be completely different. And so of course, like mapping one stateful operator to another, one set of stateful operators to another is a super difficult task. It's not yet implemented, and it's kind of not a Flink fault that it's not implemented. But knowing this doesn't make our life easier, because for us, we want to provide a platform where users want to go, update SQL, and like just relaunch the job, and it should just pick and continue working. So the typical recommendation is to always kind of backfill. So if we want to update Flink SQL, we compose the job in such a way that it first kind of run in the batch mode, already process data, and then continue on the new data. But it's really inconvenient, and it's also costly. If you want to do this every single time we update these kind of features, it will cost us a lot of money, and it's just super inconvenient because like backfill is also taking time. And so like we want the experience so that we updated the job and just relaunch them, and it continues working. And so one thing that where Flink shines is so-called data stream API. Data stream, in comparison to SQL API, data stream is where we build the job, express the job in the form like some JVM language, like Java, Kotlin, or Scala. And there is a really nice interop between SQL and data stream. So in particular, it's called changelog. When we want to get kind of from SQL to data stream, there is a thing called changelog. Basically, SQL will send so-called changelog rows. What is it? It's a row of the data with this marker, like on this, like plus I. Plus I means that it's new row on our virtual table. And there could be minus I plus minus U plus U. They come with pair. Minus U means that this was the row before update, and plus U means this is the row after update. And so once SQL is running, like it keeps issuing this kind of changelog entries. And what's interesting about this changelog, that if we look at this, we can notice that the final values of our kind of columns, our features, is aggregation over this changelog if we consider plus operation as plus and minus operation as minus. So basically, like here we see 3 rows, like, and if we want to count like shares, we do 3 minus 3 plus 5. Final result is 5. And the same continues. So like we can keep kind of treating these changelog entries like commands, either plus command or minus command. And if we want to express this in the form of this kind of data stream API, there will be a function like this, super simple. We have row update, we have current state, we get the state, and we see if it's positive update or negative update, and we perform this update. Super simple. So far, it's like super obvious. But what's interesting about this model is that it survives job upgrades. Because like when we upgrade the job, we lost SQL state, fine. But this SQL will continue issuing these changelog entries. And so we have this set of like plus I, minus U, plus U, etc. Then job upgrades, and now this row from the SQL engine perspective is new row. And so it will start sending this plus I entries. And it's fine. This plus I represent exactly the change from the previous data. So from the logic that performs aggregation over the changelog, nothing happens. So like, it just keeps treating these entries as a command, like plus command, minus command, etc. And so we see like we had this aggregation, now job upgrade happened, but we don't care. We keep aggregating these changelog entries. And so we can compose the job in this way. Like there is a SQL part and there is changelog aggregation part. And SQL part, we don't control the state there because of this magic and complexities of this SQL and so on. But in this changelog aggregation part, it's expressed in data stream, and this is where we control the state. And so we can build the state in such a way that it survives job upgrades. So this part of the job can be restored from save point and continue. And so the flow will look like we updated the query and just relaunch the job from save point. And computation will continue. So nice. Now we have the system that we can write and also update. It's pretty exciting. But the next problem that we might face is that when we launch the job, performance over time may decline. And it's clear why. We call this the job getting tired. It's clear why, because like this is stateful job. So like, and we have state, and the bigger the state, the less performant the job. It's kind of clear, pretty clear dependency. And the typical recommendation, okay, like you have the state that just apply TTL. And so like the state will expire, like, and it will be constant size, so like, the job will not get untied. It's a fine recommendation, but it's not really clear what kind of TTL to pick. For instance, in our case, we have largest tile that we use in this system is 5-day tile. And so if you want counters to be accurate, like the TTL must be at least 5-day. But it's not even entirely solved the problem of lifetime counters, where we don't have window, so it's not really clear what kind of TTL to pick. But assuming the find with lifetime counters being kind of inaccurate, and assuming we find with 5-day TTL in the context of lifetime counters, but the problem is that 5 days is too much. So in our experience, that the job processing like hundreds of thousands of events and performing like millions of operations per second with the state, it showed signs of being tired pretty quickly, like in just a few hours after launch. So 5 days is just too much. Of course, we can upscale the job, but it comes with a cost. So what we can do about that? Remember that we now have two types of the state. One is a SQL state, and now like changelog aggregation state. And the good news about SQL state that we shouldn't do anything, like because we already survived the job upgrade because of this changelog mode. And now, like from the SQL perspective, it doesn't matter if it lost state because of job upgrade or it lost state because of TTL. Doesn't matter. So we just set TTL on SQL and keep treating this changelog commands as commands. So we shouldn't do anything. And for changelog aggregation state, we can modify our function a bit. So when we access the state and it got expired, we can just query our Scilla because the data exists in the Scilla. And so like we modify, like have this in green update of our function, and now can set TTL for changelog aggregation as well, and it will kind of keep running and recovering itself from the main database. And so now the job are no longer getting tired. So it has consistent performance because the state has a consistent size. So good. Now we can launch the job, update the job, and it's not dying. The problem, though, now that with previous change, now jobs not only write to database, but also read from them. And it's actually a big deal. A big deal for the job to read from database because for database like Scilla or Cassandra or similar kind, reads are somewhat more expensive than writes, especially cold reads. So if we read something which is cold, which doesn't contain like in database cache, a lot of stuff happens because we need to scan a few multiple files on the disk to get the data, merge them, update the cache, a lot of stuff. And what's interesting about jobs, so that they are more likely to hit cold reads than the service that serves features. And so what would happen is that when we do something on the job side, for instance, we launched a bunch of test jobs. And we want to launch test jobs because we want to unlock this engineering velocity and we want to experiment and so on and so forth. Or maybe some job got a backlog for some reason and need a huge backfill or whatever. So we launch the job and they start hitting these cold reads, and especially if it's in backfill and they try to kind of process the backlog, they hit a lot of these cold reads. And it kind of thrashes main database and affects the service latency that access the features. So what to do about that? Like first thought may be that we need some kind of throttling. The problem, though, it's not really clear the level where we should apply the throttling. We cannot throttle on individual workers level in Flink job, because at least like we have multiple jobs, and new job can come and go. So instead, we can have some kind of coordinator in between jobs and Scilla, which basically kind of proxy. It's a tricky thing though, because this proxy, Scilla and Scilla clients are really super uber optimized. And so if you want the same efficiency for the reads, like this proxy should be at least optimized as well as Scilla itself, which is rather tricky. So overall, this solution is kind of complex. It actually has extra cost because we need this component, which need to be scaled appropriately. And likely it's less efficient because it's not really easy to write this proxy in the same way that it will be as efficient as Scilla itself. The second option called data centers, like Scilla, the same as Cassandra, it has data center kind of abstraction. It's purely logical abstraction. It doesn't need to be real data center, real physical. But basically, we can split our cluster into two logical data centers, and job will hit like data centers for the job, data center for the job, and feature store will hit data center for the feature store. It's pretty nice because it has super great isolation. We also can independently scale these different data centers. The downside is that the cluster management for Scilla becomes much more complex. And it also comes with the cost. Because even though we can independently scale this data center, it still means extra capacity. And also, the complexity of cluster management shouldn't be underestimated, because especially if we want real data centers, and now we have, for instance, we wanted our database to be in 2 data centers, and now it's kind of in 4. So it's like the complexity actually increases quite a lot. And the third option, the one that we ended up with, is so-called workload prioritization. There is this feature in Scilla called workload prioritization, is that we can define multiple service levels inside Scilla and attach different workloads to different service level. How does it work? So any access to any resource in Scilla has the kind of queue of operations. And for instance, we have a job queue and service queue. Like job has like 200 shares and service has like 1,000 shares. What does it mean? It means that for any unit of work for the job queries, Scilla will perform up to 5 units of work for service queries. So there is the scheduler that picks from these queues and forms the final queue. And what it means? It means like finally we will have consistent latency. Of course, job latency will be higher than service latency, but this is fine because job is background thing and doesn't care about latency that much. It cares about throughput. Service, on the other hand, it cares about latency. And so, like summarizing this final solution, how it will look like. Basically, we don't do anything with the cluster, with the Scilla itself. We just set up this different workload, different service levels. And from the job, we access the cluster using like user for the job workload. And from feature service, we access using user for the service level. And so like this is super simple. No operation overhead. Best cost because we don't need to do anything with the cluster. The only downside is that job and service, they connect to the same nodes in Scilla. So theoretically, they are not entirely isolated, but it's a nice trade-off between cost and safety. And final story is like about being lazy, so that we now we have like we can launch the job, they are running, and they don't impact our main service. And so now it's time to think about the data model in database to serve the queries. So we need to be able to serve this, to query these tiles to aggregate window counters. And the natural data model is like this. So like Scilla has the notion of partitions. Partition is basically a set of kind of rows ordered by some keys. And so we can attach each entity ID to partition, and inside partition we can store each feature in its row. So like basically feature will be identified by timestamp of the tile and feature name. And so we have this kind of rows. This schema is nice. because it is basically, we don't need to modify the schema when we add each feature. So like it's kind of schema-less in terms of like we can add as many feature types as we want, and the schema survives. However, if we do some math, we have like 8,000 feed requests. On average, we rank around 2,000 candidates. For each candidate, we need to query 100, let's say 100 features. And for these features, we need to query like 20 or something tiles. And also, assuming that our feature service has some kind of local cache, and assume we have like 80% cache hit rate, then we multiply on all of this, we will get more than 7 billion rows per second. This is the load that our database need to perform, like in order to satisfy this load. This is totally fine for Scilla. It can scale to this number, but the problem is that it will use some compute. So like, of course, kind of our cloud provider, GCP, and Scilla itself, they will be happy to scale, but our financial officer might not be that happy. And so what we can do? Instead of storing each feature into individual row, we can compact multiple features into the same row, like this, so that now rows identify only by tile timestamp, and row value is basically bytes, some serialized list of pairs, like feature name to feature value, feature name to feature value. So like this is nice because now we don't have this 100 multiplier anymore, because we will query 100 less rows, and this number of rows per second looks much better. The question may arise is whether it's really a cost saving, because it can be that we just shifted the compute from the database layer to basically the job, because we used to have this nice schema when we updated each features independently. It was nice, but now we have this combined like features, and in protobuf it can be expressed like in message like this. So we have like features combined and map in string to some feature value. And so what does it mean? It means like whenever like feature is updated, we need to kind of serialize all of them together every single time. So basically, it may look like that the cost of updating a single feature now gets like 100 times bigger. It's a fair question, and there are fairly easy steps to mitigate it. So like the first, it's a no-brainer, is that we don't need to store strings, of course. We always can store some kind of identifiers of the feature. We can always have like dictionary mapping feature values to some IDs. So now we need to serialize like mapping of int to feature value, which is of course like for protobuf is much easier. The second observation is that protobuf format is pretty nice in the sense that this map can actually via equivalent to just a repeated set of key value pairs. So basically we have two like messages, like one is features combined and another like features combined compatible, which is just repeat map field entry. And we can serialize the features combined and deserialize features combined compatible, and vice versa. So they're kind of equivalent in the form of bytes that gets produced. And moreover, they actually equivalent to the just repeat bytes features. So basically, array of arrays. And so like all these three messages, like features combined compatible, features combined lazy, they're equivalent in the form of the bytes that get produced by protobuf. So how does it help? It helps that in the fleeting state, we can store the map from feature ID to the bytes. Bytes is serialized this map field entry. And so when we need to serialize all of these features, we just combine these bytes together, have this array of arrays, form this features combined lazy message, and serialize with protobuf. And this serialization of protobuf, it's super easy because protobuf itself will just write these bytes one after another. And so like this serialization is like extremely cheap. It's much cheaper than serialization of original message. And so in fact, when we implemented that, we didn't need to scale the job at all. So like in comparison to other things that the job is doing, this step is basically negligible. And so to summarize, like assuming that you decided to build a feature platform, like first, it's good luck. It's going to be an interesting journey. Second, like take a look on ScyllaDB and Redpanda. The odds are that they may impress you and be your friends. Third thing is that Flink is still the king of real-time stream processing, but it takes time to learn and to use it in the most efficient way. And the fourth thought, like the vendors, there are multiple vendors now who build SQL-only stream processing. And my thought is that, in my opinion, SQL is not enough. I don't understand how we can build what we built without this power of Flink data stream API. Probably it's possible via some, I don't know, user-defined functions or something, but it's likely would look like much uglier and harder to maintain. So like, in my opinion, this Flink ability to have this data stream API is really powerful. And finally, lazy protobuf trick is pretty nice trick that can be used pretty much anywhere. Like for instance, in addition to this place, we also use it on our service to cache gRPC messages. So basically, we have gRPC server, and there is a cache in front of it. And so we can store serialized data in the cache. And when we need to respond to gRPC, we just send this data over, send these bytes over the buyer without need to like deserialize the message to serialize it back. So that's all what I wanted to share. Thanks for listening. And please don't forget to vote and leave feedback. Thank you.
We definitely have a lot of time for questions. Anybody have? Okay. Please wait for the mic, and also, Ivan, can you repeat the question?
Yeah.
So you're looking into C++ variants of various, well, classically Java tools. Have you looked into Viverica's new C++ version of Flink yet?
So can you repeat? I didn't get it.
So partially backed by a team at Alibaba, Viverica are launching a C++ rewrite of Flink. So it'll have similar kind of properties to like Scylla's rewrite of Cassandra and such.
You mean the question is?
Into that yet? Like I think it's called Vera, their new platform.
So you mean the question is? Like
have you looked into using that as another way to get more performance out of Flink?
Other C++ tools, you mean? Or which one?
Yes, so there's a new one called Vera by the Viverica team, which is a rewrite of the core Flink engine in C++.
I actually didn't know about rewrite of Flink engine. So the question is, have we considered some solution? How it name?
I'll tell you later.
Yeah, okay. So like the question is that there is some solution which is Flink rewrite to C++, pretty much like what happened to Scylla that rewritten Cassandra, which is Java, to C++, and Redpanda the same, like Kafka, which is in Java to C++. So in fact, I don't know about like the solution in C++, but there are other solutions that kind of claim to be Flink competitors, which is written in Rust. And the downside of all of them that I mentioned, they claim to be all SQL only. And this is harder. So like we took a look on multiple of them. Performance may be indeed good, but how to adapt them with the same level of what we can do with Flink, we didn't manage to figure out. So that's the question. If someone can show, maybe I'm personally totally open-minded about other solutions.
Thank you for the great talk. I just have a question for, can you comment a little bit on the developer experience of adding new features and how often does that happen? So you said you have 100 features, how often does that grow? and what's the developer experience of that? Thank you.
Yeah, okay, thanks. The question is about the developer experience of adding features, how it looks like in our solution. So it's far from great, to be honest, but it pretty much like we have for each features, we have some kind of configuration file. We split features into so-called feature set. Feature set, they are logically combined. Logically, like, for instance, we have one model and like user features for this model or this kind of stuff, like post features for this model. They are somehow logically combined. And this configuration file is basically YAML that contains some settings and also query. Query in Flink SQL, but the query is simple, so like it's equivalent in any SQL dialect. And this query is basically select, blah, 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 and then people can do something with select, like transform something, whatever. So they define the query, and then basically they can launch the job. So that there is deployment pipeline, they can push the button and job gets upgraded. And so yeah, that's the flow to define the features. There is also the process how this feature gets available for training, and we still use so-called wait and lock approach. So like basically the feature, through the lifetime of accessing the feature, we log the values, and using this lock, like model gets trained. So like there is process. So like when we edit features, we now start to access it for login, then enough time passed, so like model can start being trained on this data.
Can you maybe elaborate on why did you choose Red Panda over Kafka?
So like for the cost. The question is why we chose Red Panda over Kafka. The answer is the cost. So that we basically, first of all, we wanted managed, to be honest, like because we didn't want to manage. We didn't have people to manage Kafka. So we used experience to manage Kafka in-house. It just didn't have team to continue this. And then we started evaluating the solutions. So like there is Confluent and other vendors. And then we compared prices. And Kafka was the winner for the cost. But also there are a few other considerations, like they have like remote read replicas, and they kind of moving towards being data lakehouse. Every vendor actually moving to that direction, but like their vision we just liked. That's all.
A very quick question. So the data stream API for Flink is very similar to Spark structured streaming in terms of the ability to do upserts on the tables. I was just wondering if you have any best practice advice regarding, so if jobs fail, we can use the checkpoints to trigger jobs. But what about the disaster recovery strategies if the data is lost? Like what usually have you kind of thought in terms of like a data backup, but then the trouble becomes that the checkpoints are not portable to another location because of issues of hard coding of the table IDs and stuff like that. So have you kind of thought about that?
Mm-hmm. The question is about the best practices of using Flink or Spark streaming, which is equivalent, in terms of disaster recovery. Like if job died or something happened. First of all, we have checkpoints enabled. And they actually taken pretty regularly, like once per minute. So checkpoints gets uploaded to cloud storage, S3 equivalent in GCP. So we have a history of checkpoints, and also we take save points once in a while. So we have all this stuff ready to job to recover from. But sometimes, to be fair, with Flink, at least, actually the state can get corrupted. And the state can get corrupted in such a nasty way that like all checkpoints that we store, let's say we store like last 5, 10, whatever checkpoints, they all can get corrupted because like the corruption can propagate from checkpoint to checkpoint. And so now we have the job with unrecoverable state. What we do, And the good thing about the approach I described, that we don't do anything, we just start job from scratch, because it will just restore, like recover from the main database by itself. There will be some, a little bit of incorrectness, probably, due to like last minute or whatever of data, but in general, it can get to the running state pretty quickly.
Great talk. I have a follow-up question to the developer experience. I can imagine that when you're trying to understand, especially the part where you talk about the changelog and the Fling operators, as a developer, I would love to be able to interact with the state. I'm wondering whether, I know that the queryable state feature from Fling was deprecated. I don't know whether you were able to figure out a different way to see what's within the state and help you in your ability to create new features and stuff. Thank you.
Yeah, great question. Thank you. The question is about developer experience when it comes to figuring out what's going on inside the job. Basically, we have like state, actually two states. One is SQL state, and then this changelog, aggregation of a changelog. What to do? It's in the works now for us. Like we didn't have this for a while. Relied on like basically feature log already down the line. So like when feature computed and access it, we log it, and we can have basically match rate over like raw data plus feature logged. Yeah, of course it's pretty tricky. And what we actually want to dump this intermediate changelog operations to some OLAP database like ClickHouse or similar. And in this way, we will have this full history of what happened and ability to query and see. But it's not yet ready, so like we are working on it now.
Thank you. Thanks everybody. Let's give one more.